Hi, in this video we are going to see the linearity of Laplace transform. In other words, we are going to show that Laplace transform is a linear operator, mapping any function to its Laplace transform. Okay, let us start with two functions or two signals, x1 of t and x2 of t, with Laplace transforms. Okay, x1 of t has the Laplace transform x1 of s with region of convergence denoted by ROC1. Okay, remember, for the Laplace transform, the expression is not sufficient. You have to give the expression as a function of s, but together with the expression, you have to define the region of convergence. Okay, so x1 of t has the Laplace transform x1 of s with region of convergence shown by ROC1. x2 of t is another signal with Laplace transform x2 of s, and its region of convergence is shown by ROC2. Okay, now we ask the following question. If we form a linear combination of the two signals, x1 and x2, that means we multiply x1 of t by a scalar, x2 of t by another scalar, and add them, can we claim that the Laplace transform exists? So, what can we say about the Laplace transform of x of t, defined as alpha 1 x1 of t plus alpha 2 x2 of t, where alpha 1 and alpha 2 are arbitrary scalars or constants, let us say. Okay. Now we have here, we have to pay attention to the following. If region of convergence belonging to x1 of s and similarly region of convergence belonging to x2 of s have empty intersection, then the Laplace transform does not exist. Okay? Laplace transform of, we have the first observation, Laplace transform of x of t does not exist if the intersection of the convergence regions is the empty set. Okay, if the intersection of the region of convergence of the two sets ROC1 and ROC2, if they have non-empty intersection, then Laplace transform of x of t exists. So, Laplace transform of x of t, that is capital X of s, exists if the intersection is not empty. Okay, what can we say about the region of convergence? The region of convergence of X of s is, here we have two different possibilities, is equal to ROC is equal to ROC1 intersection ROC2, or the second possibility, the region of convergence is a set which contains the intersection. So we have a larger set, in other words. Now, why do we have such a possibility? It seems that the region of convergence is the intersection, but in certain cases we will see that the set may be, the region of convergence of x of t may be a larger set than the intersection of ROC1 and ROC2. Okay? Now let us illustrate all these points, but before that we have to okay, so if x of s exists, it is given by the expression x of s equal to alpha 1 x1 of s plus alpha 2 x2 of s. That means we have the linear combination of the signals x1 and x2, and when we evaluate the Laplace transform, we have the same linear combination. Okay? Well, proof of this is very simple. This is in fact trivial, since Laplace transform operation is integration and integration is a linear operation. Okay, integration is a linear operation, therefore the proof is quite trivial. All you have to do is substitute alpha 1 x1 of t plus alpha 2 x2 of t in the Laplace transform integral. That means x of s is equal to, from minus infinity to plus infinity, alpha 1 x1 of t plus alpha 2 x2 of t e to minus st integrated with respect to t. So this is equal to alpha 1 from minus infinity to plus infinity x1 of t e to minus st integrated with respect to t plus alpha 2 the integral x2 of t e to minus st integrated with respect to t, which is equal to alpha 1 x1 of s plus, okay, let us write it over here, alpha 1 x1 of s plus alpha 2 x2 of s. Okay, so this is the rather simple explanation of the fact that Laplace transform operation is a linear operation. That means linear combinations are preserved. The linear Laplace transform of the linear combination of two signals is the same linear combination of the Laplace transforms. Okay. However, we have also concluded that in certain cases the Laplace transform of the linear combination may not exist. And if the Laplace transform exists, then there are two possibilities. Either the region of convergence is the intersection of the individual region of convergence belonging to x1 of s and region of convergence belonging to x2 of s, or it may be a larger set which contains this intersection. So let us see these three cases by means of examples. Okay, so let us see the examples. The first example, okay, let us define two signals, and each signal has a Laplace transform, but we will not be able to find the Laplace transform of the linear combination, of any linear combination of these two signals, because the region of convergence of the first signal and region of convergence of the second Laplace transform of the second signal will have empty intersection. Okay, x1 of t is e to t u of t. Okay, we know that x1 of s is equal to 1 over s minus 1, and region of convergence is all those s such that real part of s is greater than 1. Okay, this is the first signal and its Laplace transform. Okay, the second signal, let us choose a signal with a Laplace transform such that the region of convergence will have empty intersection with the first one. Okay, x2 of t is minus e to minus t u of minus t. So this is left-sided. x2 of s has the Laplace transform 1 over s plus 1, but the region of convergence, okay, region of convergence for x2 of s is all those s such that real part of s is less than minus 1. Okay, for any alpha 1, alpha 2 arbitrary constants, Laplace transform of alpha 1 x1 of t plus alpha 2 x2 of t does not exist. Since the convergence regions, the region ROC1 and ROC2 will have empty intersection. Okay, the second case is now x1 of t is e2 minus t u of t. So x1 of s is 1 over s plus 1, and region of convergence is all those s such that real part of s is greater than minus 1. And x2 of t is, okay, minus e to t u of minus t. x2 of s will be 1 over s minus 1, and the region of convergence will be all those s such that real part of s is less than 1. Again, we have a right-sided signal x1 and left-sided signal x2. But now the intersection of ROC1 and ROC2 is not empty. So, Laplace transform of alpha 1 x1 of t plus alpha 2 x2 of t is alpha 1 x1 of s plus alpha 2 x2 of s. This is x of s, in other words. So x of s is alpha 1 divided by s plus 1 plus alpha 2 divided by s minus 1. Okay, and the region of convergence is the intersection of ROC1 and ROC2. So it is all those s such that real part of s is greater than minus 1 and less than 1, or in between minus 1 and plus 1. So it is the strip on the complex S-plane, which is the region of convergence and which is the intersection of the two convergence regions belonging to x1 of s and x2 of s. So the first example was about the case where the Laplace transform of the linear combination does not exist. In the second case, the Laplace transform of the linear combination exists, and the region of convergence is the intersection of the individual convergence regions. The third example will be about the case where the region of convergence of the linear combination will be a larger set, a set which contains the intersection of the individual convergence regions. Okay. Okay, x1 of t is u of t. What is the Laplace transform of u of t? It is 1 over s, and the region of convergence is all those s such that real part of s is positive. Okay. Now, x2 of t is, let us choose it as u of t minus 1. So, the unit step signal shifted by 1 unit to the right. Okay, so what is x2 of s? It will be from minus infinity to plus infinity, u of t minus 1 e to minus st integrated with respect to t. So this is, in fact, u of t minus 1 is 0 for t less than 1. So the integral will start from 1 up to infinity, and there the value of the signal is equal to 1 e to minus st integrated with respect to t. Okay. Now, if we write it as the integral from 1 to infinity, 1 e to minus sigma t e to minus j omega t integrated with respect to t, it is clear that this integral is finite, or it exists if sigma is greater than 0. Again, the region of convergence is sigma greater than 0, and the integral is minus 1 over s e to minus st evaluated at 1 and infinity. At infinity, it vanishes, so it is, because sigma is greater than 0, we have chosen the region of convergence as the region sigma greater than 0, the half plane. Okay, so we have e to minus s divided by s as the Laplace transform. The region of convergence ROC2 is again all those s with real part of s greater than 0. Okay, now there is no space here, so let us see the linear combination u of t minus u of t minus 1, which is a finite duration pulse, which is equal to 1 from 0 to 1. Okay, we know that finite duration signals, when they are absolutely integrable, of course, they have a Laplace transform, and the region of convergence is the entire S-plane. So here, region of convergence for x1 of s is all those s with real part of s greater than 0. Similarly, for x2 of s, we have the same region of convergence, so the intersection will be the same set. All those s with real part of s greater than 0. However, in the linear combination, we have a region of convergence which is the entire S-plane, which is a larger set, which includes the intersection. Because we will see that the singularity at s equal to 1 is removed. Okay, it's a removable singularity. Okay, so since we have no space here, let us discuss these next. Okay, x1 of t is equal to u of t, and its Laplace transform is x1 of s equal to 1 over s, with convergence region defined as s such that real part of s is positive. Okay, x2 of t is u of t minus 1, and x2 of s is e2 minus s divided by s, with convergence region all those s such that real part of s is greater than 0. So we see here that the intersection of the two regions is, again, since they are equal to each other, they are equal sets, we have the same set. Now let us define x of t as x1 of t minus x2 of t. So is this a linear combination? Yes. Alpha 1 is chosen as 1 and alpha 2 is chosen as minus 1. So this is a linear combination, therefore, and since the intersection of the two convergence regions is non-empty, we know that the Laplace transform will exist. But x of s is 1 over s minus e to the power minus s divided by s. Okay, x of s is equal to 1 minus e to minus s divided by s. Now again we ask this a question similar to the question we have considered for finite duration signals. Is s equal to 0 a pole? The answer is negative because x of s is 1 minus. Now we can expand the exponential function in terms of a Taylor series expansion. Minus s plus s squared divided by 2 factorial, etc. Okay, divided by s. Now these ones will cancel out and we will have s divided by s is 1. Then we have s divided by 2 factorial, and then we have the higher order terms, s squared, s cubed, etc., which means that s is a removable singularity. So the singularity at s equal to 0 is removed. So s equal to 0 is a removable singularity. So region of convergence of x of s is entire S-plane. So we have the case where the region of convergence is now a set which includes the intersection of ROC1 and ROC2. Okay, so it's a larger set. The region of convergence is a larger set. Okay, well, the reason for this is that x of t is in fact u of t minus u of t minus 1. Therefore, it is the pulse 1 for t between 0 and 1 and 0 otherwise. So x of t has finite duration. And we know that finite duration signals, if they are absolutely integrable, of course, they have a Laplace transform, and the Laplace transform exists for all s. The region of convergence is the entire S plane. So this is the complete discussion related to the linearity of Laplace transform. Thanks for watching.